So this is chapter 15, conjugated systems. Our conjugated systems are going to focus all on dienes. So di means two, ene is a suffix we use to talk about alkenes or double bonds. So a lot of the concepts we'll be introducing in chapter 15, we should really be familiar with because we already had chapter 7, which was all about the characteristics and the identification of alkenes. However, in conjugated systems, now we're going to introduce a second double bond, whereas chapter 7, we were only studying alkenes from the perspective of only one double bond. So conjugated double bonds is whenever we have a compound and our double bonds are separated by only one single bond. So an example of this would be 1,3-pentadiene. We see that our compound is separated by only one single bond at the carbon 2 position. Where isolated double bonds, they're going to be separated by two or more single bonds. So an example like this would be 1,4-pentadiene. Cumulated double bonds are not separated by any single bonds. This is whenever we have two carbon-carbon double bonds back to back. So if we were to have 1,2-pentadienes, cumulated double bonds are of very high energy. They're very unstable. But make sure you know how to identify conjugated, isolated, and cumulated double bonds. Make sure you're also familiar with the relative stability of alkenes. And we're going to compare these stabilities by using heats of hydrogenation. And so this is something that we already saw in chapter 7. And in chapter 7, we used the concept, the more substituted our alkene was, then the more stable our alkene. Therefore, we would expect to have a low heat of hydrogenation. So, our molar heat of hydrogenation and stability or substitution have an inverse relationship. As we increase in stability or as we increase in substitution, we have a decrease in our heat of hydrogenation. Whereas if we were to have an increase of our heat of hydrogenation, then this would indicate that we have a very unstable molecule or that we would have a very unsubstituted alkene. However, now that we're introducing cumulated, isolated, and conjugated double bonds, we need to know their order of stability as well, where our cumulated dienes are going to be a very high energy, very unstable. This was from slide 5, and then so we also introduced our alkynes, where terminal alkynes were the next in line for the most unstable, and then internal alkynes. So I did want to throw that in there, but really focus on our dienes, where we have cumulated dienes, and then isolated dienes are going to be moderately stable. They'll have a moderate heat of hydrogenation. And then our conjugated dienes are going to be the most stable diene group. So if we go back looking at our 1,3-pentadiene, our 1,4-pentadiene, our 1,2-pentadiene, and if we were asked to put this in order of increasing molar heat of hydrogenation, we'd want to start with our lowest heat of hydrogenation and go to our highest heat of hydrogenation. So we want to start with the most stable diene and end with our most unstable diene. So we learned that conjugated dienes are going to have the lowest heat of hydrogenation. So we could put our 1,3 pentadiene as our first compound because it's conjugated. It's very, very stable. Next, we'd have our 1,4 pentadiene as next in line for our order of stability or molar heat of hydrogenation. And then our most unstable diene, or the diene that will have the highest molar heat of hydrogenation, is going to be that cumulated diene, our 1,2 pentadiene. So that is how we should be able to rank our dienes in order of molar heat of hydrogenation, whether it be increasing or decreasing. If we have two different dienes and let's say they're both conjugated. So let me add in let's add in 3-methyl 1,3 pentadiene. Now if we were to compare all of the compounds that we see over here, we now have two conjugated dienes. And so the way that we would differentiate between these two conjugated compounds is now we look at how substituted each alkene is. So if we look at our double bond over here, our terminal double bond is only connected to one other alkyl group, so it would be monosubstituted. Whereas if we look at this double bond right here, it's going to be trisubstituted. We have one alkyl group, two alkyl groups, three alkyl groups. So we have a mono and a trisubstituted double bond. Whereas if we look at our 1,3 pentadiene, the first double bond, the one that's terminal, is only monosubstituted, and then this internal double bond between carbon 3 and 4 is disubstituted. And so because of that, because we have a tri and a mono versus a mono and a di, our tri and our mono conjugated diene will actually take the highest priority, and it's going to be the most stable, and it will have the lowest molar heat of hydrogenation. So that's what you'd want to do whenever you're comparing two dienes within the same category, whether they be both conjugated or both isolated. Take into consideration of their substitution. And overall, knowing this relationship right here, substitution and stability have a direct relationship. However, they have an inverse relationship with our molar heat of hydrogenation. So let's talk about why conjugated dienes are super stable. So as we stated, conjugated double bonds are only separated, or conjugated systems are two double bonds that are only separated by one single bond. We know that to form a double bond, you have to have an overlap of two p orbitals. And in these p orbitals, that's where we have our loosely held electrons. However, I'm going to draw my p orbitals. Maybe I should do a different color. So the average length of a single bond is 1.58 angstroms. However, due to the overlapping of our p orbitals at carbons 2 and carbon 3, we're going to kind of shrink our double bond. These p orbitals are going to draw the single bond closer. we're going to, because of the small amount of our overlap between the p orbitals at carbon 2 and carbon 3, kind of what we're visualizing right here, we're going to kind of pull that single bond a little bit more together. We're going to shrink it. We're going to squeeze it. And so in conjugated systems, the single bond that separates our two double bonds actually has a length of 1.48 angstroms. And so that is why we kind of say that our single bond has a partial double bond due to that small amount of our overlap. There's also another saying that I like. The shorter the bond, the stronger the bond. And we just went over how we went from 1.58 to 1.48 angstroms. So that is why our conjugated double bonds are going to be much more stable. And then whenever we, they're going to be much more stable compared to isolated double bonds. And then we're going to talk about allylic radicals and other allylic intermediates, and they're going to be much more stable due to our resonance and our electron delocalization. Looking at the conformations of butyl-1,3-diene. So because we have a single bond between carbon 2 and carbon 3, we can rotate around this double bond. These two conformations, we call them S-trans and S-cis, they can easily interconvert at room temperature. The reason why we say S-trans is because it looks like the actual S in the alphabet a little bit. So if we compare S-trans and S-cis, we have some mild interference between our two hydrogens on our S-cis conformation. And because of that, our S-trans is going to be much more stable. And this idea or this topic is going to be much more important whenever we go over the Diels-Alder reaction or the 4+2 cycloaddition reaction. But it's very important that we look at the substituents attached to our S-cis conformation because we already have a mild interference with hydrogens. So imagine if we were to have a methyl group where we had an extra carbon and 3 hydrogens. Then we'd have a greater interference. We'd probably have some steric strain going on here. So it's very important that whenever we are working with the S-cis conformation, that we pay attention to our groups that could potentially cause any strain or interference. So now we're going to go over the 1,2 and the 1,4 addition. This is an electrophilic addition, specifically ionic addition using hydrogenation. So this is already a reaction. This is a mechanism that we have seen in chapter 8. This is one of the first reactions that we've covered. However, again, now we're looking at two double bonds. So if I were to have 1,3-butadiene and I wanted to react it with hydrogen bromide, we're going to be very specific in the way that we're going to add our hydrogen and our bromine. We're going to add our hydrogen to the first carbon or the 1 position. And then whenever we add our bromine, we're going to see that we can do that our intermediate can be resonance stabilized. And so we could add our bromine to either the 2nd or the 4th position. So that's going to be the importance of this reaction. So the first step of ionic addition, you're going to have nucleophilic attack of your double bond to your hydrogen. And our ionic addition does follow the Markovnikov orientation. So we're going to want to add to the side of our double bond that has the most hydrogens already. So we're going to add it to the very end. in the 1 position. We're going to generate a carbocation intermediate, specifically an allylic cation. So keep this in the back of your mind, an allylic cation. I will go over the allylic position, especially essentially it's just going to be your sp3 hybridized carbon right next to your double bond, but we'll go over more examples. But we see that this carbon is sp2 hybridized, this is sp2, this is sp3 hybridized, so we would say that this is the allylic position, this is a carbocation, so this is our allylic cation, but we see that it's at the 2 position. This is going to be resonance stabilized. Resonance is something that we have covered in chapter 1. So if we're kind of to flip our double bond between carbons 2 and 3, our hydrogen would still be added in the 1st position. That's not going to change. However, we would now have a carbocation at our 4th position. And then we'd have our bromine ion, but I really want to focus on our resonance structure, what's right here in between our brackets. This right here is going to set you up for your 1,2 and for your 1,4 addition. Because our 2nd step is whenever our nucleophile or our bromine is going to attack our carbocation. So here we can see 1, 2. And then for our 2nd resonance structure, we had our hydrogen at 1 and bromine at 4. 1, 4. So this is why we call it our 1,2 addition and our 1,4 addition. So we can influence the reaction conditions, and we could determine, based off of our kinetic or our thermodynamic control, what our major product will be, how our kinetic and our thermodynamic control is going to influence our addition. For example, the kinetic control is going to be, this reaction will be performed at minus 80 degrees. So this is going to be a much cooler reaction. This is a much cooler temperature, and our kinetic control is going to favor our 1,2 addition. The reason why, we know that kinetics is all about how fast or slow a reaction is. And so at minus 80 degrees, our 1,2 product is formed faster, and the reason is our 1,2 addition at minus 80 degrees, we have a lower activation energy. And we know that activation energy, we learned this in chapter 4 in Organic 1. Activation energy is the energy that's required to start a reaction. So the lower your activation energy, the less energy you need to get the ball rolling for your reaction, the quicker your reaction is going to be. So kinetic control is at minus 80 degrees, and it will favor the 1,2 addition because our 1,2 product is formed faster. Our thermodynamic control, this is all about energetics. This is all about how much energy are we absorbing? How much energy are we giving off? Is this exothermic, endothermic? This is all about how stable our reaction is. So at our thermodynamic control, this will be performed at 40 degrees Celsius, and it's going to favor our 1,4 addition. The reason is our 1,4 product usually is going to generate a more stable, a more substituted alkene. So If we go back and if we were to compare our 1,2 addition versus our 1,4 addition, our alkene in our 1,2 addition, we have a terminal double bond, so we don't have any alkyl groups to the right side of our double bond. But we have one alkyl group to the left side of our double bond, so our 1,2 addition would be monosubstituted. Whereas if we look at our 1,4 addition, looking at our alkene, we have 1, 2 double bonds. Our 1,4 addition is disubstituted. And so that's an example where we can see that if we were to go with our thermodynamic control, if we were to go with our 1,4 addition, we'd be generating a disubstituted compound, a disubstituted alkene, whereas our 1,2 will only generate mono. So now we're going to talk about the allylic position. The allylic position is going to be our sp3 hybridized carbon that's right next to our sp2 carbons on our double bond. So I like saying sp2, sp2, sp3. That is what my brain says to me whenever I'm trying to identify an allylic position. Our allylic carbocation and our allylic radical are going to be stabilized by resonance because of those loosely held electrons in our p orbitals in our double bonds. But the reason why our allylic position is just going to be a little bit more favorable, a little bit more stable, is because of that extended overlap of our 3p orbitals, and that's how we could stabilize our allylic position. So I'm just going to draw a few examples, a few compounds, and we're going to go over identifying the allylic position. So usually whenever you have a terminal double bond, you're only going to have one allylic position. So if I look at the first structure I drew, this carbon over here is sp2 hybridized. Carbon number 2 is sp2 hybridized. And right next to that double bond, this carbon right here, carbon 3, is sp3 hybridized. So we would say that this is an allylic position. I'm going to kind of fix my double bond in this example. Let's look at this internal double bond. Usually whenever you have an internal double bond, you're going to have more than one allylic position because you have two different sides of your chain that you could look at. So keep that in mind whenever you see an internal double bond. Always look both ways. So here we have sp2, sp2, sp3. This would be an allylic position. And then read it the other way. We just went from left to right, read it right to left. We have sp2, sp2, sp3. So this compound has two allylic positions. Looking at our ring, sp2, sp2, sp3, this is an allylic position. Reading the other way, sp2, sp2, sp3. So go on ahead and take a look at this example and try and identify all of your allylic positions. But our allylic position should be at the top part of our ring, at the bottom part of our ring, and our methyl substituent. So this example has 3 allylic positions. And the reason why our allylic position is important, again, we're kind of talking about how our allylic carbocation and our allylic radical, these intermediates, are stabilized by resonance. And that's exactly what we saw right here, right? This would be our allylic cation, and it's going to be stabilized by our resonance. However, there's a reaction called a free radical allylic bromination. So this is going to be a free radical reaction. We know that radical reaction requires a peroxide to form our radicals. However, with free radical allylic bromination, we're going to be abstracting or be focusing specifically on that allylic position, and it's going to require NBS or N-bromo-6-cinnamide. And it's just going to keep our Br2 concentration very low, because if that concentration of our Br2 gets a little bit more out of hand, then you're going to start to generate a whole bunch of crazy side products. So the first step in a free radical chain reaction is using a peroxide to generate your radical. I'm not going to do that. Your second step now if this is our substrate, and right here, NBS will be a dead giveaway that this is going to be a free radical allylic bromination. So before we start even removing hydrogens or adding or removing from our substrate, the first thing we need to do is identify our allylic position. So sp2, sp2, sp3. So this would be an allylic position. sp2, sp2, sp3. This would be another allylic position. Because our ring has a line of symmetry, it doesn't matter which allylic position that we pull from. So I'm going to be pulling from the bottom carbon. So after you use your peroxide to generate your bromine radical is going to abstract a hydrogen. Again, this is a free radical chain reaction, meaning that we're moving an odd number of electrons around, which is why you need to use your half arrows. So we're going to show that we're going to make a bond between our hydrogen and bromine, and then the other electron that exists between our hydrogen and our ring, that looks ugly, is going to become our allylic radical intermediate. So we've done nothing to our double bond. All we did was remove a hydrogen and generate the allylic radical. So this is a secondary allylic radical. I am not covering it in this video, but make sure you look at the order of stability of your normal carbocations and normal alkyl radical and your normal radical intermediates compared to your allylic radicals and your allylic carbocations, because they will be more stable, again, due to your resonance energy. And going to the whole point of our allylic radicals are stabilized by our resonance, that means we definitely should have a resonance structure. So we can have this secondary allylic radical. However, we could form a double bond between these two carbons. And we could create a radical right here. And that's exactly what we'll be doing right now. So we moved our double bond right here and added our radical. And that is how our allylic radical can be resonance stabilized. Identifying our second resonance structure, this is secondary as well. So whenever we add our Br2, I'm going to add it to both structures, but we're going to see that it doesn't really matter because we'll be generating the same product. So we're going to add a bromine where our radical was in the first resonance structure. And then we're going to add our bromine our second radical structure was, or our second allylic radical was. So these are both 3-bromo cyclohexene. So these are both the same structure. However, if we were to have two different structures, then we would compare to determine if we had a major or a minor product. We would look at how substituted our alkene is. You'd look if you're comparing, maybe an isolated or a conjugated diene. However, this is not a diene, but again, know how to identify how stable an alkene is, whether it's just an isolated double bond, whether we're talking about dienes specifically. But that is how you do your free radical allylic bromination. Now we're going to talk about the Diels-Alder reaction. The Diels-Alder reaction can also be called a 4+2 cycloaddition, and the main point of this reaction is we're going to form a 6-membered ring. In order to form this 6-member ring, we're going to need a diene and our dienephile. So our diene is going to have 2 double bonds, and our diene is going to be in the S-cis conformation. Now, at the beginning of this video, we stated that the S-trans conformation of 1,3-butadiene is it's stable, and in our S-cis, we have mild interference. And because of that mild interference, it's a very high energy, it's very reactive. We would not really be able to use the S-trans conformation because it's so stable that it would probably not react, or it'd be such a very slow reaction. But our diene needs to be in the S-cis conformation. Di-2-ene double bonds. We see that we have 2 double bonds, and we know that a double bond holds 2 pi electrons. So our diene has 4 pi electrons, and then our dienephile is only going to be made up of 1 double bond. So this is only going to have 2 pi electrons. And that's why in our diene, our 4 pi electrons, our dienephile, our 2 pi electrons, that's why we can also call this a 4+2 cycloaddition. This is a concerted reaction. And what's going to happen is you're going to need 3 arrows. Your first arrow is going to be from your dienephile to your diene, then your diene to your dienephile, and then also we're going to move this carbon to stand up. And what's going to happen I'm not a color coder, but let me go ahead and color code. So our arrow from our dienephile to our diene is going to form this bond, therefore getting rid of our double bond, and we'll only be left with the single bond between our dienephile. The bond between, or the arrow going from our diene to our dienephile is going to form this bond right here. So we can see how these 2 arrows alone, we have merged our 2 parts into one, creating that 6-membered ring. Now, before I go over the importance of this arrow right here, of moving this double bond, or actually I'm going to go over it right now. So if we were to leave our double bond right here, we already have 2 hydrogens at the end of our double bond, right? Terminal double bonds have 2 hydrogens. So this carbon would be connected to 1, 2, 3, 4, 5 hydrogens. And then we'd only have one hydrogen right here. And then we have no hydrogens right here. So this bottom carbon would be making, this would not be satisfying our, we would have one hydrogen down here. So this carbon would not be satisfying our tetravalent rule. This carbon right here would be satisfying our tetravalent rule. And this carbon would not. It is not possible to have 5 bonds connected to our carbon. And so for that reason, that is why we have to create or move that double bond from our diene and have it standing up. Because now if we look at the 2 carbons that it's connected to, now it's going to satisfy our tetravalent rule. 1, 2, 3, 4. 1, 2, 3, 4. I didn't draw any substituents on our dienephile, so let's go on ahead and do that. I'm going to let's do another example. I'm going to add a methyl group to our diene. And a methyl group to our dienephile. We know that this structure right here is our diene because it has 2 double bonds, 4 pi electrons. We know that this is our dienephile because it only has 1 double bond, so it holds our 2 pi electrons. So same thing, you need your arrow going from your dienephile to your diene to your dienephile, which is going to show your 2 rings coming together. And then you're going to have to move your bond, your double bond in your diene, to have it stand laterally, so that way it can satisfy the tetravalent rules. So we have a methyl group coming off of our diene. We moved our double bond to stand up. This bond is our dienephile. Coming off of our dienephile, we have our 2 hydrogens on the bottom carbon. And then on our top carbon, we'll have a hydrogen and a methyl group. So now I want to talk about whenever our dienephile has an electron withdrawing group. So an electron withdrawing group, this is going to be a little bit more important for chapter 16, but essentially whenever you have substituents in any cyclic structure, whenever it's electron withdrawing, we're going to kind of pull that electron stability and energy away from our ring. And so some common electron withdrawing groups are going to be your carbonyl group or a nitrile group. And so whenever you have an electron withdrawing group attached to your dienephile, it should be in the down position. And the reason why it's going to point closer to the carbon-carbon double bond of the diene, giving it a more stable, a more favorable position. This down position can also be called the endo position. So let's actually go over an example where we will have a bridged cyclic compound. So if we look at our cyclic structure with our oxygen, this is going to be our diene. We have our 4 pi electrons. 1, 2, 3, 4. And then if we look at our dienephile, that's going to have our 2 pi electrons because we only have 1 double bond. So if you're given a diene or a dienophile that looks like this, the first thing that I would do is I would rotate my diene to where we've been seeing our double bonds like we do right here, instead of it facing the upwards position. So that's the first thing that I would do. Also, looking at our substituents on our dienophile, we have a hydrogen, a hydrogen, a hydrogen, and an aldehyde. Aldehydes have carbonyl groups. We know that this is going to have an electron withdrawing group. So again, the first thing that I would do, I would rotate our structure, and then just keeping in mind that we have that aldehyde, that we have that carbonyl group. It's still going to be the same concept, where we're going to have a bond from our dienophile to our diene, specifically to this carbon right here, and then from our diene to our dienophile. And then we're going to have that double bond from our diene that we're going to move to the next carbon, so that way we can satisfy our tetravalent rule. So I'm going to draw this structure planar first. So we're still going to create that 6-membered ring with our double bond right here. On our top carbon, we're going to have 2 hydrogens. And our bottom carbon, we're going to have that hydrogen and that aldehyde. Right here, we really can't, because this is planar, we can't really tell the difference between our up and our down position. Also, I want to take a look at this oxygen right here. This oxygen is connected to our diene by these 2 carbons. And these 2 carbons that are going to be connected to our oxygen is now going to become our bridgehead. So this is what our structure looks like planar. However, if we were to get a more 3D structure, we have our oxygen bridgehead, we merged our 2 structures together to form a 6-membered ring. 1, 2, 3, 4, 5, 6. We definitely have a double bond. On our top carbon, this would be our down position. This would be our up position. We only have 2 hydrogens. However, whenever it comes to our bottom carbon, we have our up position, and that's where we want our hydrogen, and our down position is where we would want to add our aldehyde. We want it in that down position or in the endo position. Either way, we want it down. If we were to have our aldehyde on our top carbon. Then that means that for our top carbon, this would be our up, this would be our down position. So we would still want our hydrogen going up and our aldehyde going down. And then we'd have our 2 hydrogens attached to that bottom carbon. So that is going to be the importance of the presence of electron withdrawing groups. And so that is going to conclude Chapter 15. If you have any questions, please feel free to reach out to me.